So here we're looking at the reverse, I guess, is the process we've been looking at so far. Obviously still has some very strong links, but central limit theorem suggests that if we complete a repeated sample, a non-biased sample repeatedly, the data forms a normal distribution, correct? We can assume normality providing that NP and NP, or 1 minus P, are both greater than 5. The mean of that distribution is centered around the mean of the population, so the population proportion, and the variance is given by P1 minus P over N, which means our standard deviation is simply the square root of that. So we used our understanding of that to look at the other day. We had a population mean, a known population mean of 179, and we wanted to know what's the likelihood of getting a sample proportion that was 178. The mean of our sample proportion being 178. And we looked at that and it gave us 14% or whatever it was, and we used our normal distribution to determine the probability of that occurring. Now that's a great example, but what's the problem with that example? Do we often know the population's proportion? No. No, we don't. What is a lot easier to get, the sample proportion or population proportion? Sample proportion. We don't often do polls straight after elections because we know the population proportion, so we don't need to do a poll. But we do often do a lot of polls leading up to elections so we can find out what's going to happen. This process that we're looking at, confidence intervals, is saying, well, now that we've done a sample proportion, how likely is it that the population proportion lies within a range? So if I do a sample proportion and I find out a value, I want to know with what certainty does the actual value of the population, so the actual representation of the population, sit, and how confident can I be about that? So just off the top of our head, what do you think would help? What's the easiest thing or the clearest thing I can do to get my sample proportion close to my population proportion? What's the easiest fix to get as close as possible? If I sample one person, big sample size. So the bigger the sample size, the more reliable the results. Here I've got an example, we're going to use this in our understanding of Z-scores and to create confidence intervals. So we understand that we can create a normal distribution. We're going to use Z-scores to say, well, how confident can I be? If I wanted a 95% confidence, what would my Z-score be, approximately? 2. If I want a 99.7% confidence, 3. And if I want a 67%. What I want you to do now, you're going to need your calculators. Tell me the Z-score required for a 90% confidence interval. Don't write, I need you to follow along here. Give me the Z-score for a 90% confidence interval. And if you don't know how to do this, you need to make sure A, you're trying, and B, you take some feedback on it in a few seconds.
The variance.
I don't need to tell you anything about the variance. I said, don't worry about the question. Give me a Z-score required for a 90% confidence interval. That's all. I've given you all the information you need. Alright, hint 1. What kind of distribution are we dealing with? Normal distribution. We can apply a normal approximation because we've got NP greater than 5. And in 1 minus P. It is. James has got it, it's 1.6, but I'm going to let you keep going. Until you see that number on your screen, you need to keep going. So it's a normal distribution, correct. What do we know about this normal distribution? Do we know an upper limit or a lower limit? Yes or no? We don't know an upper limit or an upper, so we're not going to be using NCD. NPD is a complete waste of time. So what button are we hitting? Inverse normal, correct. Inverse normal. Let's think about the type of distribution that I want, or the type of tail. So on left tail, do I want a right tail, or I want a central? I can use any of them, but what's the most likely? You can use any of them, but I'd probably go with the central tail, personally, or no tail. Central. What's the area in which we're dealing with here? What type of tail is best? So you're
That's one.
a 90% confidence interval. We want a 90% confidence interval
Yeah.
for a Z-score. And you've gone inverse normal,
Yeah.
and you've gone
Central.
central.
I just don't know what numbers.
Yep, so we know you're at the same point as everyone else.
Oh.
We know the area that we're dealing with. What's the confidence we want? 90%, which is area 0.9. I set it to Z-score, so what does that tell us about this? Standard deviation is? And then mean is? You go to the top, make it variable. And we get plus or minus 1.64. Cool. You could have done it with the left tail. Do it with the left tail now.
Mean 0 won't change.
Well, you need to change your area when you're doing a left tail.
Oh.
0.95 or 0.05. Either will work.
Why not 0.10?
Because 10 implies there's 10% each side. Sweet. Okay, so we know our Z-score for 90%. We need to be able to do that on our own. Now, I've done that intentionally first because we're about to deal with another normal distribution and I don't want us getting caught up in the process. So, there's two separate processes here. Sometimes we have to find our Z-score using a normal distribution, using an inverse norm. That distribution is separate to the one that we're about to look at. So, we're going to look at an example. We've got 70 out of 100 people prefer to shop online. Determine the 95% confidence interval. And that's all the information you need. What do you think if I put, I'm not going to say, if I put you in a situation where I was going to give you $1 million if you could identify the population proportion, what would your guess be? So 70 out of 100 people prefer to shop online. What is your best guess at the population proportion? 70% or? 70% or 0.7, sorry, 0.7, cool. That's your best guess. Are you certain the population proportion is 70%? No? What would make you more certain?
Check them.
More samples, correct, would make you more certain. If I asked you to give me a range of values where you thought the population proportion would be, you can't say 0 to 100. Within a reasonable amount. If you were to pick a 10% buffer, what would your buffer be? 0.65 to? 0.75, very, very good. So we're setting our buffer, and that's the confidence interval. It's our little buffer that says, how wide can we be before we're pretty confident that we've got our...
So where are they getting these numbers from?
Yeah, where
Yeah.
is that number from?
Like
What?
why the numbers that everyone's saying? The buffer thing, like how do they know that? Where's this coming from?
I'll teach you. So this is our sample, 70 out of 100. And we're going to create a confidence interval where we say, well, I want to be 95% certain that the population proportion is within that range.
And you get 0.05 either side, actually.
Well, I'm just giving you a value. In their situation, I just said 0.5 each side.
Yeah, that's what I was
Yeah, but I hadn't given you a confidence interval. That's just me saying, if you had a 10% buffer, which way would you go? But this process allows us to determine the buffer that we actually need. Sweet. So the first thing we need to do is find out what's the standard deviation. Because our Z-score is describing how many standard deviations away from the mean. So our standard deviation, using the equations we had before, we shove that in and we get 0.046. Cool? Now if I wanted a 95% confidence, or 95% of my data to be held within, how many standard deviations do I need? 2, approximately 2. So my confidence interval is simply my middle value, which is my 7 out of 10, plus or minus my Z times my standard deviation.
What's the CI?
Hmm?
This.
What's the what stand for? Okay, cool. So here's my confidence interval. What am I going to write? Tell me what to write here. 7 on 10, which I'm going to represent as 0.7, just because. Plus or minus 2 times.
And we know the Z scores 2
Because this is what tells me my Z score is 2.
Yeah, because
What if it was like 90?
If it was 90, 2 becomes 1.64.
Had to figure it out. So you
Yeah.
just put it up.
Yeah. In reality, it's not 2, it's 1.96. We just approximate to 2. Cool. See, if it's tech active, you'll need to use your calculator to find your
Where
Z.
did the 96 come from?
That's if you did the 95%, that's actually what the Z score is. I'll just leave it at 2 for now. Okay. Don't get confused.
yeah, but that's for the central cell.
We want a central, yeah.
Yeah.
We want 2 each side. Because we don't know if our population proportion is less than or greater than the actual value of sample. So we're just going, we're going to go each side by the same amount. So 0.7 plus or minus 2 times that, which gives us 0.7 plus or minus 0.092. So my confidence interval, I'm 95% sure that my scores occur between 0.608 and 0.792. So I'm 95% sure that that's the case. Now, if I was dealing with a medical procedure, and a medical procedure that potentially had impacts on someone's life, would you be happy with a 95% confidence interval? Probably want a bit more, correct? What would you want? 99.9? I'll probably want a bit more, but we can go with 99.9. 99 point whatever, right? So you want a lot of confidence when you're dealing with those. If I'm dealing with the likelihood of someone hitting a dart behind their back at the local pub on a Friday night or whatever it happens to be, do I need a 95% confidence interval?
No.
No.
30.
Probably take a 30. Probably take a much lower confidence interval, whether it's 75% or 90% or whatever it happens to be. Cool. So we change our confidence interval in reality based on how much we need the data to be accurate. Cool. Let's say I want really accurate data, and I'm not happy with a 10% swing or a 20% swing on my confidence interval. What could I do? What could I do to reduce the size of my confidence interval here? Up my sample size, sample more people. Cool. So rather than doing 70 out of 100, I could do 700 out of 1,000 people. Then I'll be much more certain. Now the last thing in red, I've got that circled. That's given us, no, don't worry. That's given a special name. Thank you for ruining my punchline. We call this the margin, I called it a buffer before, but that there is our margin of error. Okay, and it's often given E or ME, and that is equal to Z times the square root of P1 minus P over N. And what is that? What is this part here? What do we call that? That is our standard, well that is our standard error, which is our standard deviation. And the Z represents our Z score, which tells us about what? How many standard deviations, the number of standard deviations away from the mean we are. Cool? One more thing. If I gave you this data point, could you tell me, I'm going to give you a different data point. Could you tell me the confidence interval, and could you tell me the sample proportion, looking at just that?
Yeah, it's in the equation.
How can you tell me, so I might give you some numbers here. Give me some numbers, we'll go, it's between 0.55 and 0.75.
So how do you have small ones?
This one? Says minus that. So that's the minus, and that's the plus.
So is the 0.7 is the 7?
Yep, the 70% that we started with. Cool. So what do you think here, looking at this data, what do you think my sample proportion is? Have a guess? 5, 4, 3, 2, 1, 0.65. How did you get that?
In the middle.
It's halfway between these two. Just average them out. Cool. Do we get that? And what's my margin of error there? 0.1. How do you get that? How many margins of error are in here? How many margins of error? There's two. There's one below and then one above it, correct? So we just subtract the two, then divide it by 2. The difference between them divided by 2. Or you could do that minus one of the values. It doesn't matter. Use this, you'll be fine. Good? Why is everyone looking concerned?
How did you get the margin of error?
So what's the difference between these two? 0.2? 0.2? And there's two margins of error in there. The first margin of error to the proportion, the second margin of error to the top end. So it's just that divided by 2. Or, there's two ways of doing it, that's one. The other way is saying, well that's my middle value. Subtract one of those from, subtract that from my middle value.
And how is it 1?
0.1.
How is it 0.1?
Because 0.65 plus 0.1 is that. And 0.65 minus 0.5 is that. Cool? Capiche? Everyone's happy with confidence intervals? So you're finishing off exercise 10.3, and that was question 2 to 10. If you've done that, question 1 to 3.
Would we have to find out like the percentage confidence interval for like data points?
Would you have to find a percentage?
Like the Z score?
You may. You may. Cool. You can do that though.